First, I'd like to thank the organizer for the invitation, and it's a great opportunity for me to share my recent topic on this tissue engineering. So in this conference, I guess I don't need to introduce heart failure or heart attack, but I still use 2 slides to introduce how severe it is that will lead to the solutions we are working on right now. So just look at the south of the border, and each year almost 8,000 people suffer from a heart attack. And this is good news and bad news. Good news is more than 80% of patients suffer from a heart attack can survive. The bad news is those people has a major cardiovascular problem. And one major problem is cardiac arrhythmia. I can say that can lead to the heart failure, but immediately problem is cardiac arrhythmia. So how severe is cardiac arrhythmia is? Each year at south of the border, 350,000 people die of this sudden cardiac death. And most people died due to arrhythmia. And 80% of those people died due to arrhythmia had the MI before they have a cardiac sudden death. So why this arrhythmia and MI is related to this sudden cardiac death? So we know in the heart there's 2 major functions. One is contractile function, and squeeze the blood into the circulation. To make that heart working well, the heart had to have this electrical propagation that will make the entire heart organize, working together to squeeze the blood out. But when the patient had a heart attack, cardiomyocytes died and replaced by the scar tissue. And this scar tissue will increase the external resistance, and the electrical propagation will go zigzag and not go to the normal ways, and that will lead to the cardiac arrhythmia. So isn't it a good solution to solve that? So let's come back to visit what happened after myocardial infarction. And you can see the cardiomyocytes is isolated, surrounded by the fibrotic tissue, and that will result the normal conductive propagation not go through that well. So last few years, we working on the conductive biomaterial, and we thought if we put the conductive biomaterial into the injured area or into the fibrotic tissue, if we can reduce the external resistance, that will synchronize the cardiomyocytes working together, and that will diminish the arrhythmia. So that's what our hypothesis. So now, first we have to look, what is a conductive material? Before we talk about the conductive biomaterial. Conductive biomaterial is a unique molecule. It's polychain, and each structure have this unique characteristics. They have a single bond, double bond, single bond, double bond. And this double bond has 1 electron. It's not that stable. When you're doping this material, 1 electron will be out, and then the other electron flow around. That make the material can become conductive. So this conductive material can working really well, but we cannot use in the biological system because they are not biofriendly. If you have this conductive material in the membrane or in the piece of tissue, they are very rigid. It's very hard. If you put into the heart, and there will be broken heart. To solve that problem, first step, a few years ago, we have this conductive biomaterial, and then we conjugate that material into the biomaterial. That's called a chitosan. And then we cross-link the polypyrrole chitosan into the hydrogel, and then we can plate cover the culture plate. So first we did is immobilize conductive biomaterial into the conductive material into the biomaterial to generate this conductive biomaterial. It's a little bit confusing. So after we have this conductive biomaterial, we design this device. So we have So we have this device. We coat the culture dish with a control group that's chitosan or conductive biomaterial. We want to test this conductive biomaterial can pass electric current. So what we did is we put 2 pieces of skeletal muscle into this dish, and dish has no liquid, no other material can pass a current. And one side of the muscle, we put the electrical stimulator. And the other side, we use EMG, electro muscle graph, to recording the voltage. So when we gave the different stimulation, that's x-axis, and then we can see the other side of the muscle receiving the action potential amplitude. And you can see the muscle in the conductive biomaterial, they can receive the stronger the conductive velocities, conductive voltage compared with a control group. That means conductive biomaterial can pass biological electron to the other side of the muscle. So we have this biomaterial, how conductive it is. So we use this 4-probe machine to measure the conductivity of the conductive biomaterial. We find it's 3 times higher compared with a control material. So now we have the conductive biomaterial. We want to know if we add the conductive biomaterial into the matrix, whether that will change the extracellular matrix conduction or not. So my student, Daniel, sitting there, what he did is he created this extracellular matrix. We use a gelatin, created extracellular matrix. And then we created the multiple different compositions mixed with a conductive biomaterial, 9 to 10, 9 to 1, and 8 to 2, and 6 to 4, 2 to 8, and then pure conductive biomaterial. We want to measure the voltage pass-through or conduction of this material. So what we have is we have different composition, and we have the conductivity. In the control group, the gelatin will have very little conductivity, but the conductive biomaterial is very high. With the increase the conductive biomaterial in the matrix, we can increase the conductivity of this mixture of the extracellular matrix. So those data we generated by using the electrode to stimulate the material. So that's man-made stimulation. But we want to know whether this conductive biomaterial can truly pass through the biological voltage through the material and to the next cells or next heart. So what we did is we create this insulator. And then we loaded the insulator with the conductive biomaterial. At the bottom, we cut the holes. We use a multi-electrode array to measure the voltage in this conductive biomaterial. And then we take the red heart, we perfuse the heart, and put the heart beat on top of the conductive biomaterial. And then we look at the voltage received by the MEA. So we use the same system, and we use a extracellular matrix with a different mixture with the conductive biomaterial. We look at the MEA received field potential amplitude That's a microvolt. And we can see with the increase of the conductive biomaterial in the matrix, we can see the voltage is much higher received. So we create this material, and we can see the material can carry the conductions. But a lot of people said in the cardiomyocytes, the action potential generated by the cross-membrane and sodium-potassium. But in your biomaterial, there's no sodium potassium at all. How this current can pass through from the heart through the material can be censored by the MEA. So working with Professor Song Yu, and he's a postdoc fellow, we use this physics electrical circuit to evaluate the entire system the current can pass through. So to be honest, I don't know that too much, but I try to explain that. So what he found out resistance between the heart and the material. They also find out resistance between the material and MEA. They also find the capacitance of the entire system and resistance in the entire system. By gave the stimulation, they can calculate how much electrical current generated and passed through in this biomaterial. So what they tell me is this circuit is flow really well, and the current can go through. So with this equation, we can prove the biological current can pass through the conductive biomaterial, can pass to the next group of the cells. So then we want to know whether this conductive biomaterial can work with the cells or not. So this is my PhD student, Tri G. And what she did is she coated the cell culture dish with a conductive biomaterial. On purpose, she seeded neonatal cardiomyocytes in the very low density. The reason for that is we create the gaps between the cells. If we grow the cells in the sheets, and then the conductive velocity will go very slow, very smooth, and you will not know what the contribution of the bottom part of the conductive biomaterial. But in this study, we seed the cells in the very low density. We want to evaluate the conductive velocity. So this is what she did. She take the 3 culture dish, 1 dish seeded nothing, another 2 dish seeded, first coated with a control biomaterial, that's a chitosan, another dish coated with a PPY and chitosan. And after that, she seeded the cells in a very low density. And then she studied conductive velocity using the calcium imaging. So this is what she found out. Cells in the control group, the conductive velocity from one point to another point take long times. But the conductive velocity in the control group also spend times. But the conductive velocity in the conductive biomaterial or grow on the top of the conductive biomaterial, the conductive velocity is very fast. So we put all the data together, we find it out with the conductive biomaterial in the culture dish or on the top of the culture dish, and then you grow the cells. These cells has a greater conductive velocity, even they have not connected each other. So that cells link together. What happens if you put the cells totally separate without the cells at all? So what she did is like this. She coated the dish with a different material, and then she put the metal ring over there. And then she seeded the cells inside the ring and outside the ring. And the ring were left over there, and physically separated the cells inside from outside. And then she loaded the calcium dye to look at the cells' contractions. And then she find it out. Just look at this. The outside ring, the cells beat regularly, and inside the ring, cell beat at a different rate. So this is two lines, black line and the red line. They show the inside cells, outside cells beat at different rate. But if you look at the cells grow on the conductive material, although the cells physically separated by the metal ring, but the inside cells and the outside cells still beat synchronously. So those are the in vitro study. Now, if this material can work inside of the animal or inside of the heart, so this is a PhD student and the postdoc fellow working in the lab. So we use an adult rat. First, we create the myocardial infarction, and you can see the scar tissue at the left ventricular free wall. 1 week after myocardial infarction, we inject the conductive biomaterial into the damaged area. So we have 4 groups, normal, MI, and with a chitosan and PPY chitosan. I just want to show you the picture of this. And you can see we inject the conductive biomaterial into the damaged area, covered entire infarct region. So first we want to know what about the action potential or field potential at this area. So we know that every heartbeat, the current pass through, and you can use a sensor to sensor the action potential of each field. But when we put the MEA onto the scar tissue, we can feel very low voltage on the surface of the scar tissue. But when we put the MEA on the top of the scar tissue with the conductive biomaterial, we can feel the higher field potential. So that means more current pass through the scar tissue after we put the conductive biomaterial over there. So we use MEA to do this map, and we can see when we measure this conductive propagation in the control group, and you can see this current pass through the halfway from the normal tissue. When they reach to the border zone of the scar tissue, this conduction cannot go through. But if you look at this, when we inject the conductive biomaterial into the infarct region, and you can see this voltage can go through the infarct region to reach entire the heart. So this only look at the region. How about the entire heart? So we did another study, and this study we use this multi-electrode catheter to measure. So this is a 8 leads catheter to sensor the conductive voltage. So what we did is we put 2 leads. We suture this catheter on the top of the surface of the heart. We put the 2 leads at the normal region, 2 leads at the border zone, and 2 leads put on the scar tissue. And then we record all these action potentials. And then you can see this is a normal heart, and all the 6 leads or 8 leads have the same action potential. And at infarct region, normal tissue have the higher voltage, and at infarct region, they have very low voltage. So that means our system working well. And then we put it into this study. We look at in the control group, the normal region is normal, but infarct region is very low voltage. But when we look at the control group, the material control group, they show the similar results. But when we put the 2 lead at the scar area with the conductive biomaterial, the voltage is pretty high. We use this normal region as a denominator, calculate the ratio, and we find it out. The scar tissue with a conductive biomaterial, that region has a higher action potential compared with no treated group. So this is just a voltage dye to look at the entire heart, the conductive propagation, and we find it out after inject the conductive biomaterial, the propagation going really well. So all this in vitro study and in vivo study showed the conductive biomaterial can reduce the scar tissue resistance, but whether that really can reduce arrhythmias. So now we did the study. So when we try to inject the conductive biomaterial to reduce arrhythmia, the people said, if you put it over there, you may initiate arrhythmia because you put the conductive biomaterial into the heart. That might be the problem. So what we did is we did the telemetry in the rat. We did the 72 hours recording, and this is the heart rate monitor. We find it out the heart rate did not change after we injected the conductive biomaterial. And to look at the arrhythmia, we find it out after myocardial infarction. This is telemetry data. We did a 72 hours monitoring. After myocardial infarction, the animal occasionally have the PVC. And injection of the material, we still can see the PVC. But the rat, we inject the conductive biomaterial, the PVC occurrence lower dramatically. So this is the data. So that means we inject the conductive biomaterial into the infarct region. That can reduce the number of the PVC after we monitored 72 hours. So why we put the conductive biomaterial can reduce the PVC? So we look at these QRS intervals. That's we look at the ECG. We find it out the animals injected with a conductive biomaterial, they shortened this QRS. We know the wider the QRS will initiate the arrhythmia, so we can shorten this QRS. That's why all these animals has a lower PVCs. And then we use a clinician use the way to evaluate the arrhythmias. So that is a program electrical stimulation. We find it out. Animals injected with a biomaterial, they have much lower prone to the arrhythmias compared with a control group. So this slide showed the function improvement. So actually, the main talk is talking about the conductive biomaterial can change the conductive velocity, so the improve the cardiac function just by given. So in conclusion, we have generated a conductive biomaterial that is a bio-friendly material. And this biomaterial can enhance or synchronize cardiomyocyte contractions. And after we inject the conductive biomaterial into the heart, we can reduce the possibility of the arrhythmia. So I'd like to thank, this is a cartoon we generated. After the patient had a heart attack, the wires are broken, and we try to use to rebuild the wires. So we have all the student fellows and working on this project. And I know Daniel is sitting over there. He did most of the in vitro works. And this collaborator, the Dr. Song, is from Taiwan. He helped us to synthesize conductive biomaterial. And Dr. Sung Yu helped us did this electrical circuit. Thank you very much. Thank you.